A newly deployed enterprise payment service is running flawlessly. Transactions are clearing in milliseconds, and the system easily absorbs the incoming traffic load. Then, at exactly the 10-minute mark, transaction latency spikes. Response time stretches from milliseconds to seconds. But strangely, CPU usage plummets. You check the dashboards. Garbage collection logs are quiet, thread counts are perfectly stable, memory heap usage is completely flat. The immediate instinct during an incident like this is to blame the database connection or scour the static source code for a bug. But as you can see in this architectural map, an enterprise Java application is a continuous, living conversation between bytecode, interpreters, compilers, and memory structures. Fixing these complex failures requires moving past the static instructions of the source code to diagnose the dynamic behavior of the runtime environment. Execution begins in the interpreter. The interpreter translates code step by step, which is safe but relatively slow. Crucially, the interpreter is watching. It tallies exactly how the application behaves in production. It counts loopback edges, tracks popular paths through if statements, and records specific variable types. Once the interpreter identifies the hot paths, the code doing the heavy lifting, it hands that profile data to the just-in-time, or JIT, compilers. This process, called tiered compilation, rewrites heavily used code into optimized native instructions. The JIT compiler starts by inlining. It collapses separate function calls into a single direct operation. Next comes escape analysis. If an object never leaves its thread, it eliminates the heap memory allocation and deletes unnecessary synchronization locks. It pushes further with devirtualization. Observing only one used implementation, the complex routing maze snaps into a straight, lightning-fast direct path. The system achieves extreme performance by literally rewriting the application on the fly, tailoring the instructions to the exact behavior it observes. Which brings us back to the 10-minute incident. Right before the latency spiked, a developer flipped a live feature flag. That single toggle changed the shape of the data objects flowing through the system and forced the execution of previously unused code branches. The JIT compiler's aggressive optimizations were built entirely on earlier observations. Now those underlying assumptions are instantly false. This triggers a safety panic called de-optimization. The system invalidates compiled native code and tears down the optimized paths. Execution is violently thrown back to the slow, unoptimized interpreter. The entire warm-up cycle begins all over again. If an application undergoes repeated cycles of compiling and invalidating, it fills up the code cache, the native memory zone where compiled instructions are stored, degrading performance further. Severe memory retention leaks, like abandoning data in pooled thread locals, can similarly choke this runtime ecosystem. These issues disrupt performance even when the core logic is technically sound. When runtime reality deviates from the compiler's strict profile, the JVM prioritizes safety over speed. The optimizations are scrapped, and you are left with severe, untraceable latency spikes. Fixing the 10-minute ghost did not require rewriting business logic or paying for larger cloud instances. This diagnostic dashboard, generated by the Java Flight Recorder, displays the exact moment the failure occurred. By reading these timelines, the team could directly observe the massive spikes in de-optimization and recompilation events. Managing this runtime environment requires strict production hygiene. You start by perfectly aligning your maximum heap size with your container memory limits, leaving enough room for native processes. You bound your local data caches and strictly cap direct memory usage to prevent silent resource exhaustion outside the main heap. In the code itself, keeping critical execution paths predictable, avoiding overly complex, highly polymorphic calls with too many possible targets, gives the compiler the stable environment it needs to do its job. Massive scale depends on mastering the runtime environment as an adaptive, living engine. Its habits and its limits must be understood.